This is lecture 13 on linear algebra, and we're going to talk about eigenvalues and the spectrum of a linear operator. So this is from the beginning in the notes of chapter 6, more or less sections 1 to 3. So if we have a linear transformation, T, from a vector space to itself, is called a linear operator. So a linear operator is just a linear transformation from a vector space to itself, and the dimension of V is n, and we have some basis W1 up to Wn. Then T is represented by an n by n matrix, a square matrix where T of the vector Wj is some summation Aij Wi. I goes from 1 up to n. So we have this n by n matrix A with coordinates Aij. So here's a picture, if you like. Here's T. Here's the vector space V, and T maps V into itself. Now it might be there's a subspace W contained in V, and T of W is actually contained in W. So we say that a subspace W of V is, and the word we use is invariant with respect to T if T of W is contained in W. What this means is that for all vectors W in the subspace W, we have T of W is also contained in W. So if, for example, W1 up to WK is a basis for W, and we extend this to a basis for V, W1 up to WK, WK plus 1 up to Wn is a basis for the whole vector space. Then for every vector in this basis, Wi up 1 up to Wk, you look at T of Wj, T of Wj, this is a sum of the basis vectors Aij W sub I, but the Wi's are restricted to the subspace. We don't move out of the subspace, so I goes from 1 up to k, not up to n. And if you look at the matrix for T with respect to this basis, we have in the upper left-hand corner a k by k square matrix, and everything under it is 0. And what's over here, k and n minus k rows. These can be any numbers, but in the upper left-hand corner, we have a k by k square matrix, and in the n minus k columns under those, only everything is 0. So that's kind of like the picture in terms of the matrix of an invariant subspace. And in fact, suppose W1 and W2 are two subspaces of V, such that every vector V in V has a unique representation in the form V equals W1 plus W2, where W1 is in the subspace W1, and the vector W2 is in the subspace W2. Then we write V is W1, and I write a plus sign with a circle around it, W2. This is called a direct sum decomposition of V. And if both W1 and W2 are invariant subspaces, with respect to V, and let's say the dimension of W1 is K, and the dimension of W2 is N minus K, then the matrix for V with the right basis looks like this. Here we have a K by K square matrix in the upper left-hand corner. Everything under it is 0. Here we have an N minus K by N minus K square matrix in the lower right-hand corner, and everything above it is 0. So it's kind of like a diagonal matrix where down the diagonal you have two small square matrices. In the simplest case, suppose our vector space is R2, and R2 is this W1 direct sum W2, where these are invariant subspaces. So they all each have dimension 1. So then the matrix will look like lambda 1, 0, 0, lambda 2. That's the matrix for T. And with respect to the basis, you would have T of, say, 1, 0. What is that? Well, lambda 1 times 1, 0, or lambda 1 times 1, 0, and T of 0, 1 would be 0 lambda 2, which is the same as lambda 2 times 0, 1. And what you see is that T of this vector is just a scalar multiple of the same vector, and T of the second vector is just a scalar multiple of the same vector. And these vectors are one-dimensional invariant subspaces. That's the simplest case of an invariant subspace, and that's actually the only case I want to consider now. So suppose we have T from V to V, a linear operator. So let's say over the reals or the complexes, a scalar lambda is an eigenvalue. That's the eigenvalue. It's a German word, but semi-German. It's an eigenvalue of T if there is a non-zero vector V such that T of V is just lambda times V. So all T does to the vector V is stretch it by a scalar factor lambda. That's called an eigenvalue. And the vector V, which is non-zero, is called an eigenvector. With the eigenvalue lambda. And the set of all eigenvalues of a linear operator is what is called a linear operator T. It was what is called the spectrum of T, or spec T is how it's abbreviated, but the spectrum of T. So there's a nice theorem or lemma, whatever we want to call it. So let lambda 1 up to lambda k be distinct eigenvalues of T, and let v1 up to vk be non-zero vectors such that T of vi is lambda I vi for all I going from 1 up to k. So these are the eigenvectors corresponding to these eigenvalues. Then this set of eigenvectors is linearly independent. Proof. That C1v1 plus C2v2 up to CK VK be equal to 0. Then T of C1v1 plus C2v2 plus CK VK is equal to 0, because T of the 0 vector is 0. On the other hand, T of C1v1 plus C2v2 up to CKVK, because T is linear, it's a linear operator, this is C1T of V1 plus C2T of V2 up to CKT of VK. And because each of these vectors is an eigenvector with eigenvalue, the T of VI is lambda I VI, this is C1 lambda 1 V1 plus C2 lambda 2 V2 plus CK lambda K VK, and that equals 0. So we have this identity, and the proof of the theorem will be by induction on K. Suppose K equals 1. So we have a vector V1 different from 0. T of V1 is lambda 1 V1, but the set V1 is linearly independent, because any set that consists of just one non-zero vector is linearly independent. Suppose K equal 2. So we have T of V1 is lambda 1 V1. T of V2 is lambda 2 V2. So T of C1 V1 plus C2 V2 is C1 T of V1 plus C2 T of V2, which is C1 lambda V1 V1 plus C2 lambda 2 V2. And suppose C1 V1 plus C2 V2 is 0, then T of the 0 vector is 0. So we have this identity. We have this identity. Let me multiply this by lambda 2. I get C1 lambda 2 V1 plus C2 lambda 2 V2 is 0. And if I subtract, these cancel, and I get C1 lambda 1 minus lambda 2 V1 is 0. So this is the 0 vector. The lambda 1 is different from lambda 2. So the only time a scalar multiple of a vector is 0 is if the scalar is 0. So we have C1 lambda 1 minus lambda 2 equals 0. But lambda 1 is different from lambda 2. Lambda 1 minus lambda 2 is different from 0. So that means C1 is 0. And if C1 is 0, then C2 V2 is 0, so C2 is 0. So the only time you have a linear combination of eigenvectors with distinct eigenvectors equal to 0 is when it's a trivial linear combination. So that's the case 2 for 2 vectors. So if we now do the usual inductive kind of argument, assume true for k eigenvectors with distinct eigenvalues. So now we take k plus 1 eigenvectors, v1 up to vk plus 1, eigenvalues lambda 1 up to lambda k plus 1. Suppose some linear combination of these k plus 1 eigenvectors is 0. Then T of this linear combination which is C1T of V1, CK T of VK, CK plus 1, T of VK plus 1, which is C1 lambda 1 V1, CK lambda K VK, CK plus 1 lambda K plus 1, VK plus 1. That's equal to 0. We started with this relation, multiply it by lambda K plus 1. We get C1 lambda K plus 1 V1, CK lambda K plus 1 VK, CK plus 1 lambda K plus 1 VK plus 1 equals 0. If we subtract these two equations, these terms cancel, and we get C1 lambda 1 minus lambda K plus 1 V1 up to CK lambda K minus lambda K plus 1 VK equals 0. But this is a linear combination of the eigenvectors V1 up to VK equals 0. So all of these are independent, linearly independent. That was the induction hypothesis. So all these coefficients have to be 0. So Ci lambda I minus lambda K plus 1 is 0 for I going from 1 up to K. But lambda I minus lambda K plus 1 is different from 0 for all these because the lambdas, the eigenvalues are distinct. So if this product is 0 and this is different from 0, Ci equals 0 for I going from 1 up to K. And if all the Ci's from C1 up to CK are 0, CK plus 1 is 0. So that's a proof of this result. So in particular, just to make this very concrete, if we have T from R2 to R2, so this is a linear operator, eigenvectors corresponding to distinct eigenvalues are linearly independent, but R2 has dimension 2. So it has at most 2 linearly independent vectors. So this a linear operator from R2 to R2 has at most 2 distinct eigenvalues. And how can we find these eigenvalues? Well, let's take a look. In general, suppose T is a map from a vector space V to itself, and we have an eigenvalue, or let's say lambda is an eigenvalue if and only if there exists a vector V different from 0 such that T of V equals lambda V. So to say that T of the vector is lambda times the vector is the same as saying that T of the vector is lambda times the identity operator times the vector, because I of V is just V, which is the same as saying that T of V minus lambda times the identity vector applied to V is 0, which is exactly the same as saying that T minus lambda I of V is 0, and V is non-zero, which is exactly the same as saying that the kernel of the linear operator T minus lambda I is not the 0 vector. So suppose T is a map from R2 to R2. And suppose with respect to some basis, the matrix for T is, let's say, A, B, C, D. Then the matrix for the identity operator, of course, is just 1, 0, 0, 1. That's the identity. And what is the matrix for T minus lambda I? That's A, B, C, D. Lambda I is just lambda down the diagonals. So that's A minus lambda, B, C, D minus lambda. And the kernel of this is 0 if and only if the determinant is non-zero. An equivalent way of saying this is that there's a non-zero vector in this kernel. So the kernel of T minus lambda I is not just the 0 vector, if and only if the determinant of the matrix A minus lambda B C D minus lambda is equal to 0. And this is exactly the same as saying lambda is an eigenvalue of T. Of course, what is this determinant? The determinant is this times this minus this. This is A minus lambda, B minus lambda, sorry, D minus lambda, minus BC, if and only if lambda is the root of this equation. See, if I write this out, this is lambda squared minus A plus D lambda plus AD minus BC equals 0. So this is a very nice argument that tells us a huge amount about 2x2 matrices and linear transformations on a two-dimensional space. So we have T from, let's say, R2 to R2. Actually, it doesn't matter what the field is, but say R. Suppose T is given by a matrix A, B, C, D, then the eigenvalues of T are the roots of the quadratic equation lambda squared minus A plus D lambda plus AD minus BC equals 0. So to find the eigenvalues, we just have to solve a quadratic equation. Let's look at some examples. Suppose we take a linear operator for which the matrix is 7, 5, minus 4, minus 2. So A plus D is 7 minus 2 or 5. AD minus BC, the determinant, is minus 14 plus 20 is 6. So our quadratic equation is lambda squared minus 5 lambda plus 6. And we want to solve this. Well, this is easy. This actually factors. This is lambda minus 2, lambda minus 3. So this says we should have eigenvalues 2 and 3. Let's look for the corresponding vectors. That is, we should be able to find vectors x, y. The first one would be that's 7, 5, minus 4, minus 2. Applied to the vector x, y should just be 2 times x, y. So this should give us some equations we can solve for x and y. Let's see, what is this? If I multiply this out, this is 7x plus 5y, 4x minus 2y equals 2x, 2y. Or if I bring this over to the other side, 5x plus 5y, 4x minus 4y equals 0. So we want to solve 5x plus 5y equals 0. 4x minus 4y equals 0. See, the first equation is the same as x plus y equals 0. Second equation is the same as x minus y equals 0. If I add the equations, I get 2x equals 0, so x equals a half. And that means y equals, sorry, if I add the, yeah, so 2x is, oh, that's not right. Something's wrong here. Let me just double check. 7, 5 minus 4, 2. So A plus D is 5. AD minus BC minus 20 plus 14. Minus 14 plus 20 is 6. So this is my quadratic equation. I get eigenvalue, it factors lambda minus 2, lambda minus 3. I get eigenvalues 2 and 3. So 7, 5, 4, oh, minus 4. Let me make sure I write this out. Yeah, this is minus 4. My handwriting is just so bad. So these are both the same as x plus y equals 0. So any vector where y equals minus x. So if I let lambda 1 equal my first eigenvalue, 2, the eigenvector v1, y is minus x. If x is 1, y is minus 1. Let's just check. 7 minus 4, 5 minus 2 times 1 minus 1. This is 1 minus 5, or 2. Minus 4 plus 2 is minus 2, which is 2 times 1 minus 1. So my matrix applied to this vector is 2 times that vector. So that's the eigenvalue. And suppose I want to find an eigenvector for the eigenvalue 3. So in this case, here's my matrix: 7 minus 4, 5 minus 2. Applied to the vector xy should be 3 times the vector xy. This is 7x plus 5y minus 4x minus 2y equals 3x, 3y. If I subtract one from this from the other, I get 4x plus 5y minus 7x minus 5y should equal 0, 0. Let me just double check this again. 7x plus 5y minus 4x minus 2y should equal 3 times xy, 3x, 3y. So this is 4x plus 5y, and this is minus 4x minus 2 minus 3 minus 5y. So both of these are equivalent to the equation 4x plus 5y equals 0. So one solution would be x equal minus 4, x equal minus 5, y equals 4. So let's just check. If I take 7, 5 minus 4 minus 2, applied to the vector minus 5, 4, this is minus 35 plus 20 is minus 15. This is 20 minus 8, which is 12. This is 3 times minus 5, 4. So the vector applied to this matrix is the number 3 times that vector. So this vector is an eigenvector for the eigenvalue 3. Very nice. So this is a basic calculation, which 100% with 100% probability will be on the exam on Thursday. Look at some other solutions. Or some other problems. Let's look at this example. Suppose I take the matrix, I'll call it B, which is minus 3, 0, 5, 2. And we want to find eigenvectors and eigenvalues. Well, let me just call it A again. So I want to look at the determinant of the matrix A minus lambda I. So that's determinant of the matrix minus 3, 5, 0, 2, minus lambda 0, 0, lambda. That's lambda I. That's the determinant of the matrix minus 3 minus lambda, 5, 0, 2 minus lambda. And that matrix is minus 3 minus lambda times 2 minus lambda. Or if I like, I'd rather write it as lambda plus 3 times lambda minus 2. Oh, that case is pretty easy. I mean, this is lambda squared minus plus lambda minus 6. But you can see from this that the roots of this are lambda equal minus 3 and lambda equal 2. Let's compute the eigenvectors. So lambda equal minus 3, you want A times the vector xy to be minus 3 times xy. So what is that? AXY is minus 3502 applied to xy is minus 3x plus 5y, 2y, and we want that to equal minus 3x minus 3y. So if you equate the x and y, the first coordinates, this says 5y has to equal 0. So y is 0. And x can be anything. So xy is just x 0 or x times the vector 1, 0. So if you let v1 equal 1, 0, this is an eigenvector with the eigenvalue minus 3. That's pretty easy. What about the eigenvector for eigenvalue 2? So we have to solve the system of equations minus 3052 minus 3052 times the vector xy is 2 times xy, which is the same as minus 3x plus 5y, 2y equals 2x, 2y, which says that y can be anything, and so minus 3x plus 5y equals 2x, which is 5x equals 5y. So x equals y. So our eigenvector is anything in the form xx, or x times the vector 1, 1. So this is an eigenvector. Let's just check. Minus 3502 times the vector 1, 1 is minus 3 plus 5, 2 is 2, 2 is 2 times 1, 1. Oops, 2 times 1, 1. So this matrix applied to this vector is 2 times this vector. So here we have the eigenvalue 2. Let's look at another example. Suppose we take the matrix 0, minus 1, 1, 0. We apply this to a vector xy. We get, well, we'll get minus y plus x. But I really have to look at the matrix A minus lambda I. That's 0 minus 1, 1, 0 minus lambda 0, 0, lambda. So this is minus lambda minus 1, 1 minus lambda. And the determinant of this matrix, this is lambda squared plus 1. And what are the roots of this? Well, lambda squared plus 1 has no real roots. So if we consider this matrix as the matrix of a linear transformation from R2 to R2, this has no eigenvalues. The spectrum is the empty set. So the moral of this story is that not every matrix has eigenvalues. Of course, if we were looking at a complex vector space, this would have eigenvalues lambda equal I and minus I. But if these are complex. But if we're only looking at real eigenvalues, there are no real eigenvalues for this matrix, and the spectrum is the empty set. There is none. So that's an important thing to remember. And that is all I needed to say. So you can do the homework that's due on Wednesday. Okay, that's it.